Okay, so we have the same setup here, but we're going to be comparing not the acceleration, but we're going to be comparing the velocity directions for these blocks. So part A asks, is the magnitude of the normal force exerted by the block, by the track at location A greater than, less than, or equal to the normal force at location B? So before they asked us for B and C, and now they're asking us for A and B. So let's figure this out. Here at point A here, we're on a straight road path, I should say. The normal force here is oriented like this. Our normal force here, our gravity here. Now remember from our inclined plane section that our normal force here is mg cosine theta. Okay, we drew that triangle. If you don't remember that, go back and review your inclined plane. At point B, we learned that from last problem, it's equal to mg plus mv squared over r. Remember, you feel heavier when you're at the bottom of a loop like that. So since cosine theta is going to be less than 1, we have our normal force here is less than mg. Here our normal force is greater than mg. And that's our answer for point A, part A, excuse me. Okay, now in part B, we're going to describe the relative angle between the direction of the block's velocity and the direction of the block's acceleration at all of those times. So let's start at point A. At point A, he's not moving in a circle, it's just moving straight down the ramp. The acceleration is also straight down the ramp. So for part A, they are parallel. At point B, now we're moving in a circle, okay? Am I going to draw a free body diagram? I'm not sure. There's mg, there's my normal force, okay? My net force is towards the center of the circle. Therefore, my acceleration is also towards the center of the circle. However, what's the direction of my velocity at that point? The direction of my velocity at that point is tangent to the circle. So at point B, they are perpendicular. I was too lazy to finish that. Okay, now at part C, just like in the last one, the answer that we're getting to is it's really neither. It's neither perpendicular or parallel. So right before we get to part C, my velocity is still tangent to the circle. Okay, anytime you're moving in a circle, your velocity at that point is tangent to the circle. But what about my net force and therefore my acceleration? Well, here's the normal force, here's gravity, here's my normal force, right? So my net force here is going to be somewhere off in that direction, okay? Now, the way I've drawn it, it looks like it's tangent to the circle. It really shouldn't be. It should probably be a little bit more this direction. Anyways, the answer here is that they're neither, right? Neither perpendicular nor parallel. So here's the rubric for this part. 1 point for saying that the velocity is always tangent to the track. Tangent, right? Parallel to the track. 1 point for relating the acceleration to the net force. 1 point for saying the acceleration at point A is along the track, parallel to velocity. 1 point for saying at point B the velocity is perpendicular to the acceleration. 1 point for saying that acceleration and velocity near point C are neither parallel nor perpendicular. And then 1 point for the paragraph. Okay, now just like last time, they're going to say, wait, we're going to have a collision now. The scenario is repeated with an identical block at rest. When the block at the top of the straight section of the track is released from rest, it slides down the track, collides elastically with the identical block, and comes to rest. All of that's critical, okay? We'll come back to that in a minute. The identical block then slides up the ramp. Is the maximum height reached by the identical block greater than, equal to, than, or less than? And the answer is it's equal, okay? 2 things tell me this. Number 1, there's an elastic collision, okay? Which means that the speed of this block coming in, right, and the speed of this block leaving, okay, means I'm not losing any energy, okay? But I need one more piece of information to find the speed of this block. And what they tell me is that this block comes to rest, which means it transferred all of its kinetic energy to this guy, which means now this guy's just going to go up to the MGH that this block would have gone on to if that block wasn't even part of it. So we needed both of those, okay? here's just another idea. If this block would have bounced back, what would happen? Well, this block would have even gone higher, right? Because this would have given all of its momentum plus a little bit more, and it would have had even more kinetic energy. So there was a lot going on in that problem, and you've got to dot all your I's and cross all your T's. Because it's an elastic collision, no energy was lost. Because that first block came to a stop, we know that the second block had the same amount of energy. And then we're back to conservation of energy, making it go all the way to the top. So hopefully that question was easy. That's it for the Unit 5 QQTs.